Chapter 8, Subsidence and Soils. Welcome back again. Subsidence and soils may be one of the lesser-known natural hazards we face. I find it fascinating that this hazard is so ubiquitous, so costly, and so unthought of. I bet that this hazard is happening in your backyard right now. And if you don't have a backyard, then I bet it's happening in your parents' plot of earth. This hazard rarely happens all at once. Sinkholes are the exception. But it still happens fast enough to cause damage to the majority of structures everywhere. Sometimes we call this damage settling, as in the house is just settling. But if you don't know it yet, you will know that some of that settling is due to subsidence and soil volume change. 8.1 Soil and Hazards. Soil to soil scientists is solid earth material that has been altered such that it can support rooted plant life. Soil to engineers is any solid earth material that can be removed without blasting. In the image below, would soil scientists and engineers be able to agree the person is holding soil? I think so. You can see roots in it, and obviously it wasn't blasted to bits prior to being picked up. In addition to causing some hazards, the study of soil aids in evaluation of natural hazards. In the image below, you can see a soil profile with obviously different layers of sand or of soil. The deeper horizon is buried soil, while the upper portion is sand and silt emplaced by a tsunami. What are some other hazards that you can think of that might leave a record in the soil? So think like a hazard and think like a soil. If any hazard disrupts the surface where soil is, the soil will likely preserve a record of it. Earthquakes? Yep. Volcanoes? Yep. Flooding? Yep. Landslide? You bet. If you can't explain how these hazards leave a record in the soil, go back and listen to the old lectures. Or ask me via email. Soil is produced through rock weathering and organic matter decay. The weathering process is both physical and chemical, meaning that the rock is both physically broken apart and chemically altered. An example of physical weathering is in the top right picture. This boulder has been broken in pieces, probably as water entered cracks, froze, and expanded, breaking the rock. This weathering process is called frost wedging. Unfortunately, this happens to roads as well. The image in the bottom right is an example of chemical weathering. Once again, water is involved, but this time the important component in the water is bicarbonate acid, which slowly dissolves the calcium carbonate in the rock, again along cracks and fractures. This also happens in some marble and limestone statues. This weathering process is called dissolution. In both cases, the weathered material, i.e. the rock, stays in place, meaning residual. The weathered material could also be transported, for example, by a stream. The weathered inorganic material needs the addition of decayed organic matter to get what we'd recognize as good gardening soil. But to an engineer, it's all about whether it needs blasting to be removed. Soil development depends on climate, topography, parent material, i.e. rock type, time, i.e. age of the soil, and organic processes. In a well-developed soil, there are many soil horizons, or layers of different types of soil that you can see. A soil profile is formed from several horizons. We will go through the soil horizons a few different ways to remember them. But first, let's just go through the list. The O horizon is entirely of plant litter and other organic material. O for organic. The A horizon is both organic and mineral material. The E horizon is a light-colored layer leached of clay, iron oxide, silica, and calcium carbonate, and other minerals. I remember E is for bleaching. The E horizon is the bottom layer of the zone of leaching. The B horizon, or BT horizon, collects materials leached from top layers. This horizon is enriched in clay, iron oxide, silica, and calcium carbonate, and other minerals. This is the top of the zone of accumulation. The oxidized iron it accumulates often makes this layer rather reddish, like rust. The BK horizon accumulates some calcium carbonate. The K horizon has carbonate that fills the pore spaces, often forms in layers parallel to the surface, hard and whitish. Caliche is an irregular accumulation or layers of calcium carbonate, also known as hardpan. Might need to get a rock hammer to get through it. I remember K is for caliche. Spelled different but has the same sound. The C horizon is the parent material partially altered by weathering processes, and the R horizon is unaltered parent material, consolidated bedrock. I remember R is for rock. The soil horizons A, B, C go from top to bottom, or more surface to more underground. Their composition kind of just makes sense to me based on the layers next to them. If you have a good way to remember them, please share. So, something to remember, this is not a complete list of all the types of soil horizons, just the more major ones. And something else to remember, not all soil profiles have all the soil horizons. It depends on the climate, topography, parent material, i.e. rock type, time, i.e. age of the soil, and organic processes. Remember the last slide. In this image, we have another soil profile. What horizons do you see? Pause the video to give yourself a moment to get your thoughts together. Granted, this is just an image. If we have the real soil profile here, we might change our answers. But what do you see just based on the image? The picture is of actual soil, has 4 soil horizons identified, A, B, BK, and C. No O, E, K, or R. The R horizon is probably just not in the picture. In this next image, we have another soil profile. What horizons do you see? Pause the video to give yourself a moment to get your thoughts together. Granted, this is just an image. If we have the real soil profile here, we might change our answers. But what do you see just based on the image? I see a dark, organic, rich O layer. An A layer beneath that, which is still dark, but has some dark clay-like clumps in it. Beneath that, I see a reddish layer that says to be B horizon. Below that is some lighter colored soil with some white areas, perhaps from calcium carbonate, which would make this a BK horizon. And below that, I see some gravelly-like horizon, which is weathered material, i.e. the rock that has been weathered. Here's the same profile with the image labeled. Did you get similar soil horizons for similar reasons? The next 2 images have beautiful E horizons. The leached horizon is leached of its color, so it's gray-white. Not much rusty iron oxide here. It all went down to the redder B horizon. Can you see that red B horizon in both images? Below that is the C horizon. The image on the right with the red knife also has a clearly delineated O and A horizon. The O horizon is a bit red-browner, while the A horizon is a bit darker brown. You can kind of see the same delineation on the left image. It just isn't as clear. These images show some awesome K horizons. White, hard, and even have small caves in the right image. K for caliche. Caliche forms in semi-arid and arid regions as water that contains dissolved calcium and carbonate evaporates, leaving the calcium carbonate precipitate. Here in the Nampa Meridian Boise area, we have some caliche in our soils. The depth and the thickness is variable. Ever come across caliche while digging around? Tell me about it via email if you'd like. Soil texture. Soil horizons. Hardpan, Oak-lip, hard compacted soil horizon. Composed of compacted and/or cemented clay with calcium carbonate, iron oxide, or silica. Impermeable. In the image below, it is orange, where dissolved iron has precipitated. Cemented iron hardpan in soil. Soil color can be an important diagnostic tool for analyzing a soil profile, but can be misleading. O and A horizons are dark. E horizon is white. B horizon varies from yellow-brown to light red-brown to dark red. K horizon varies from light to red. K horizon may be almost white. Soil color can also indicate drainage. For example, oxidized iron is redder and indicates well-drained soils. Reduced iron is dark gray or black and indicates poorly drained soils. Drainage relates to slope stability and septic tank suitability. Soil texture depends on proportions of sand, silt, and clay-sized particles. Clay is defined as sediment with a diameter less than 0.004 millimeters. Silt is larger and has a diameter between 0.004 millimeters and 0.074 millimeters. Sand is even larger, with a diameter between 0.074 and 0.2 millimeters. Sediment that has larger diameters are called gravel, cobbles, or boulders. Soil texture is important in determining strength and drainage characteristics of the soil, which is useful in determining what the soil can be used for. The soil texture just concerns the sand, silt, and clay portion of the soil. So after getting rid of any boulders in your sample, you would sort out the sand from the silt from the clay, either by mixing it up with water and letting it settle out over a few days, or shaking the soil through a set of calibrated sieves for a day or so. Then you get the percentages of each and then plot it on this nice trilinear graph. How do you ask? Well, I will show you.